Hey, I'm Max, and this is a 2D ray tracer I've built. I want to explain what that means and what's going on with all these shapes and colors. You might have heard of ray tracing if you're into games or graphics. It's a technique that can generate realistic images of 3D scenes, but is usually relatively slow and expensive to run. And it works by simulating the physics of how light rays scatter off surfaces or travel through materials, and this makes it particularly impressive for scenes with lots of transparent or reflective objects. When you're learning about ray tracing, you spend a lot of time staring at diagrams and equations like these. So they show how we calculate the color of a pixel in the image by working out the path a light ray would have taken to reach the camera lens at that point, and what color it would have picked up along the way. And I thought it would be interesting to make an interactive version of these diagrams that shows how we can build a one-dimensional image of a two-dimensional world. And here it is. We have a 2D world containing a camera and a single green circle. This bar at the left represents what the camera sees. So right now it's looking at the circle, so it sees green. And if we rotate it so it's not looking at the circle, it sees the black background off at infinity. So this is essentially giving us a single pixel image. If we want more pixels, we have to cast more rays out from the camera. And if we cast them out at different angles, we get perspective. So the closer the camera is to the object, the larger it appears, and vice versa. And from now on, I'm going to hide these dotted lines indicating rays that fly off to infinity because they just slow the simulation down. And so far, our image looks pretty flat. So let's add some lighting. So we'll go back to just one ray and add some annotations to the diagram. Where the ray hits the surface, we'll draw a solid line representing what's called the normal vector at that point on the surface. So that's just the line sticking directly out from the surface at that point. And we will also draw a dashed line representing the direction our ray would go if it reflected off the surface at that point, just using angle of incidence equal to angle of reflection. Now we'll add a light source to the scene, which we can drag around. We want to know how strongly this light source is illuminating the circle at the point the camera is looking at. And we use a really simple model for this at first. We draw a line from the surface point to the light and measure the angle between that line and the normal vector. If they're parallel, the light is shining straight onto the surface, so it should be fully illuminated. If they're perpendicular, the surface shouldn't be illuminated at all. To be more precise, we're multiplying the color intensity by the cosine of this angle. Now let's add more rays back in and see the result. I think the surface starts to look curved and solid, even with just this very simple lighting model. If we want to add some extra oomph, we can make the material shiny. If the line from the light source aligns very closely with this reflection vector, and the material is smooth, then much of its intensity would bounce off the surface straight into the camera lens. So we add a big dose of the light's color to the final perceived color. Doesn't that look nice? And if we do everything I've described so far in one more dimension, then we'd have an image like this now. And if we have multiple objects in the scene, maybe with different colors, we need to adjust our lighting calculation to handle shadows. So when we draw those lines from surface points to the light source, we check if that line hits any other surface before reaching the light. If it does, the point is in shadow and we don't add any lighting contribution. Of course, we might have multiple lights, in which case we just add up their contributions. And we can even change the color of the lights and see how they interact with the surface colors. And here's a 2D image with multiple objects and shadows using just the techniques we've covered so far. But I said earlier that ray tracing shines when rendering reflective or transparent objects. So let's make this green circle reflective, and we can see the reflection of the pink circle behind the camera. The more reflective the green circle is, the more of this pink color we see. And the diagram shows roughly how we're calculating the final image. We cast the initial rays out from the camera, they hit the green circle, and we calculate what color it would appear without reflection. But since it is reflective, we cast these secondary rays out along those dotted reflection vectors, calculate the color where they hit the pink object, and then add these two contributions together, weighted based on how reflective the object is. And of course, there's no reason to stop at 2 reflections. Although we do need to put some limit on the number of reflections to handle unrealistic situations like holes of perfectly reflective mirrors. Now for some transparent objects. Here we're pointing a single pixel camera at a solid orange rectangle. As we make the rectangle more transparent, we start to see the blue of the background behind it. We can also see how the light changes direction when entering and exiting the material. As you might know, this is called refraction, and the amount of bending depends on a property of the material called its refractive index, which we can change. And most transparent materials are also at least partially reflective. Each time a ray hits the edge, either from inside or outside, it's split into a refracted ray and a reflected ray, each of which contributes something to the final perceived color. And because we simulate refraction, we can simulate extremely basic telescopes or magnifying glasses. So here we have a pink circle behind the green one, and as we make the green circle more transparent, we start to see the pink circle through it. And because of the way the green circle bends the light rays, the pink one appears much closer than it actually is. Also, it's just fun to create a light show from all these reflected and refracted rays. Jumping up a dimension one more time, here's an image you can create once you've added reflections and refractions to your toolbox. And that's everything I wanted to show today. If you want to play around with the simulator, I'll put the link in the description. And I'll also link my GitHub if you want to run it locally and hack around with the lighting code. If you'd like to learn more about this stuff and build your own ray tracer, I'd recommend this book, The Ray Tracer Challenge by James Buck. It's how I learned this stuff and what I followed to build both my 2D and 3D ray tracers. Finally, I want to shout out the Recursive Center. It's an educational retreat for programmers, and I built most of this project during my time there the last few months. If you'd like to work on your own projects and become a better programmer, I'd really recommend applying. Okay, I'll see you whenever I have more stuff to show you.